Welcome back. The last few videos we were looking at the solutions of second order linear ordinary differential equations which are without non-homogeneous terms. So, basically homogeneous equations of second order linear equations. So, if you are given one solution, so you know how to find other solution, or if it is a special form of equations, if your equations are of a special form like constant coefficients or special variable coefficients like Euler Cauchy equation, you know how to find two linearly independent solutions. Okay, this is what you learned. So, few methods how to find two linearly independent solutions. Okay. So, once you know these two linearly independent solutions, if you are given a second order equation, second order linear equation with the non-homogeneous term. So, that means you have a non-homogeneous second order linear equation if you are given. So, we will also see how to find the general solution of a non-homogeneous second order linear equation by considering the general solution of the homogeneous equation and a particular solution of non-homogeneous equation. So, in this video we will give you the method of variation of parameters. This is called the method of variation of parameters to find a particular solution of a non-homogeneous second order linear equation. Okay. So, if you know y1 and y2 which are two linearly independent solutions of the homogeneous equation, you can make a linear combination of this. So, and then vary these constants c1y1 plus c2y2, you make a linear combination, and now you vary these constants c1 and c2 as functions of x. This form you look for a solution of a non-homogeneous equation as in this form c1x into y1x plus c2x into y2x. So, if you by substituting this you try to find suitable functions c1x and c2x, so that will be the particular solution of a non-homogeneous equation. Once you get this particular solution, you can combine it with the general solution of the homogeneous equation, and that together will be general solution of the non-homogeneous equation, because already two arbitrary constants c1 and c2 in the homogeneous general solution will be also there in this general solution. So, general solution means you will have two arbitrary constants because it is the second order equation. So, this is what we will see in this video. So, you will be learning what type of equations, what are the special type of equations for which you can actually find the two linearly independent solutions, so that you can find the general solution as a linear combination of these two linearly independent solutions of the homogeneous equation. So, for start with Euler Cauchy equation, where it is a special form of equation variable coefficients. Variables are simply polynomials, y power, so nth derivative, for example second derivative will have a coefficient some constant times x square, first derivative dy by dx will have a coefficient like a constant times some x, okay, constant times x. So, with this form, it is called the Euler Cauchy equation. You will know how to solve this, how to find two linearly independent solutions. Basic idea is to convert this equation into an equation with constant coefficients for which you know how to find the solutions, okay, two linearly independent solutions. I also give later on, so afterwards we give special certain equations which this technique may not work always. What the technique is to convert the second order equation into a second order equation, but without having a first order term. So, while doing that, so this reduction is called the putting into normal form or reducing into standard form or normal form. So, when you do that, when the reduced form, the normal form or standard form, if it becomes an equation with constant coefficients, or in a simpler form which you can find the two linearly independent solutions, then you can find the general solution of the given equation. Okay. So, for some equations it works. So, I give you the technique how to reduce the equation into putting the equation into standard form and then solve it. Okay. So, let us start. We will see how do we solve, we will see today how we solve this second order linear ODE with non-homogeneous term. Right hand side is given. So, what you know is the solutions. You know now how to solve second order linear homogeneous equation. Okay. So, assume that you know that, okay, you know how to solve it. You know only with constant coefficients. I have given two examples where you can, with the equation with constant coefficients, you know how to solve, how to find the general solution. Also, if it is a general equation with the coefficients are variable coefficients, but if I give you one solution y1, you will find the other linearly independent solution as y2, and then so that you can make a general solution as a linear combination of this y1 and y2. Okay. So assume that, but in general you do not know how to find your y1 and y2, only certain forms we will see that, okay, what kind of forms you can get your y1 and y2. So that is homogeneous equation, okay, second order linear ODE with homogeneous, only its non-homogeneous term is 0. If the non-homogeneous term is there, how do you find the general solution? So from the existence theorem, the equation second order linear ODE with non-homogeneous term will also have unique solution. So that means it will have a general solution. General solution means I should give 2 arbitrary constants involved in it. Okay, how do I get that? So let me do this: y double dash plus px y dash plus qx y equal to some fx. So this is your equation. Okay, if this is your equation, so you know how to find the homogeneous solution. If I write like this, y homogeneous of x, if I write this homogeneous plus some particular solution yp of x, okay, where if I do with y h satisfies y double dash plus px y dash plus qx y equal to 0. This is homogeneous solution. So this will satisfy the homogeneous solution, homogeneous equation, and yp of x satisfies the equation. So given equation, suppose you know that the given equation has some solution, okay, some particular solution. I will give you the methods how do you find such a particular solution if you know homogeneous solution. Okay. So this will satisfy the equation. So given non-homogeneous equation equal to fx for some is, then y dash, if you substitute this into the equation, y double dash plus px y dash plus qx y, what is this value? Substitute here. So yh double dash plus yp double dash plus px y dash yh dash plus yp dash plus qx y plus yh plus yp. So you collect these terms, this will give me, because yh satisfies the homogeneous equation, this will be 0 plus yp double dash px into yp dash other term qx into yp dash, because it satisfies the second equation, this will have fx. So together yh, so combination sum of this yh and yp will satisfy the actual equation. That will have 2 arbitrary constants because yh has 2 arbitrary constants. Okay, this will have 2 arbitrary constants since, okay. So this implies yx equal to yh of x plus yp of x, where yh of x is, assume that you know that you can find a general solution of homogeneous equation, some y1 and y2x are 2 linearly independent solution, then their linear combination will be the general solution of the homogeneous equation, okay, is the general solution. So the homogeneous solution plus some particular solution will be having still arbitrary constants C1 and C2. Same C1 and C2 will be arbitrary even here, okay. So that implies this is the general solution, because this has 2 arbitrary constants C1 and C2, yh has 2 arbitrary constants, same arbitrary constants. So it will be the solution of this equation, given non-homogeneous equation. Now the question is, how do I find this? You know, if you are if it is a constant coefficient equation, you know how to find your y1 and y2, okay. If it is not, you should have one to find the other, okay, as of now, and you don't know how to find your particular solution, okay, yp. So I give you a method. If you know your homogeneous solutions y1 and y2, two linearly independent homogeneous solutions y1 and y2, if you know, I will get you a method to find your particular solution ypx. Okay. So, first of all, let us see now what are the methods that will get you, what are the other equations for which you can find y1 and y2. Okay. So, we have seen constant coefficients. So, now we will see other kind of equations where you can find two linearly independent solutions. So, one is Euler Cauchy equation, Euler Cauchy equation. It is a homogeneous equation that will have y double dash plus, instead of px I will have x, okay. Instead of y double dash I will have x square, okay. Instead of y double dash I will have x square y double dash. Instead of y dash I will have multiplication with x plus some y, okay, x power 0 into y 0th derivative, x power 1 into first derivative, x square into second derivative with constant coefficients. Now, we can put some constant coefficients a, b, c equal to 0. If I have in this form, I know how to find the solutions. Okay. So, what happens? A, b, c are the constants, x, because you see if you divide with x square both sides, so I will have 1 by x, y coefficient will be 1 by x square. So, y should not be equal to 0. That means, domain is either positive or x is negative. So, this is the domain in which your differential equation is given. Then I can find you two linearly independent solutions y1 and y2. Okay. So, how do I do this? So, one simple transformation, what I do is I will use some z, I will change the independent variable x into z. Okay. So, this is the method of changing independent variable. So, change the independent variable x to some z that is given as log x. This is the transformation. So, that is you choose let z equal to log x. If you do this, what happens to your dz by dx? 1 by x dx, right? 1 by x, this is simply 1 by x. This will not help me. Okay. So, I want to replace y dash dy by dx in terms of dz by dx. Okay. So, I want to replace dy by dx as dy by dz. So, if dz by dx is this, fine. So, what I get is dy by dx, but I have dy by dx. This I can write y is a function of x. Okay. If y is a function of x, x is a function of z. Okay. So, this will give me z equal to log x implies x equal to e power z. So, x is a function of z, y is finally function of z. So, I can write dy by dz into dz by dx. So, this is, but I know dz by dx, which is 1 by x times dy by dz. So, this will give me x into dy by dx as dy by dz. See, I can replace x y dash with simply dy by dz. So, what happens now? D square y by, or in operate form if you write x times d dx is actually equal to d dz. Okay. So, now if you want d square y by dx square, this finally you have to replace x square into d square y by dx square. So, this is equal to d dx of dy by dx. So, I know that. So, you take both x square here. Okay. So, if you do this, x square times d dx of d dz of same way, okay, d dz of, sorry wait, so x square. Now in the place of x d dx you can write d dz, right. So this implies d dx is minus 1 by x dt z. So you want d square y by dx square, this is d dx of dy by dx. So I can replace 1 by x dt z of 1 by x d dz of y, right. So this is equal to 1 by x. So d dz of, so you want everything in terms of function of z. 1 by x is, what is 1 by x? dz by dx, right, into dy by dz. So this is equal to 1 by x, sorry, dz by dx is equal to, what is dz by dx? 1 by x, x equal to 1 by x, x equal to e power minus z. So you can replace 1 by x as e power minus z. So I can write e power minus z 1 by x. Then I will have 1 by x times, this will be, now I can differentiate, this is because the function of z, this is a function of z. So e minus e power minus z into dy by dz plus e power minus z d square y by dz square, okay, that is it. So this is equal to, now you replace again e power minus z as x. So this is 1 by x, e power minus z is 1 by x. So 1 by x times minus 1 by x dy by dz plus 1 by x times d square y by dz square. So this is equal to minus 1 by x square dy by dz plus 1 by x square, simply remove. So you can remove, take 1 by x square minus, so this will have minus, you can put it here, so that you have plus d square y by dz square. So now from the left hand side and right hand side I can write x square d square y by dx square is equal to d square y by dz square minus dy by dz. So you have d dz and d dz minus 1 into on y, these are the two operators, okay. So dy by dz minus y, if you do one more derivative, this is what you will get, okay. So this is what you can replace. Now you replace this x square y double dash, you can replace with this x y dash, you have already seen simpler form, x y dash I can replace with this, and finally substitute, if you substitute a times in this equation, a times x square y double dash I can replace with d dz of d dz dy by dz minus y plus b dy by dz plus c y equal to 0. Now if x is x is positive, if x is positive, log x takes the values of full real line, right. If x is positive, log x is defined for all x positive, okay, that can take full real line. So z belongs to full real line, okay. So if x is positive, that is what is the case, okay. Assume that you have your equation is given for x positive. If x is negative, what you should do, your thing should be, your transformation should be z equal to log mod x, okay. So mod x is e power z, so you have to work with minus x, okay. So that log minus x, you can take it as z equal to log minus x. If z is x is negative, if the domain is x is negative, you should work with z equal to log mod x. What is the mod x when x is negative? Is minus x. So you have to work with z equal to log minus x when x is negative domain, and procedure is same. Okay. So, this is what you will get finally. So, you get this is the equation with constant coefficients. This you can solve, you know how to solve it. Simply look for y of z as e power lambda z. Z is the independent variable now. Now, you will have a polynomial in y, polynomial in lambda, and lambda equal to 0. Second order, second degree polynomial you will get, second degree polynomial you will get, that will give you lambda 1, lambda 2, whether they are same or different, you can find the solution yz. Yz as some exponential solutions, C1 e power lambda 1 z, let us take C2 e power lambda 2 z. Okay. If lambda 1 is not equal to lambda 2, if lambda 1 lambda 2 are same, you have seen already C1 e power lambda 1 z, one solution, and C2 will be z into e power lambda 1 z if lambda 1 equal to lambda 2. This is the solution in the variable z, okay, but your given equation is in terms of x, okay, or domain is in x. So, you use this transformation z equal to log x, you go and substitute in the place of z, in the place of z put it as log x. So, this will give me finally yx as C1 e power lambda 1 e power lambda 1 log x. This is actually x power lambda 1. So, x power lambda 1 plus C2 x power lambda 2 if lambda 1 is not equal to lambda 2. Okay. So, this is for x positive I am working. So, if x is negative you will have minus x power lambda 1. So, minus x means mod x power lambda 1, okay, if x is negative. So, this will be C1 x power lambda 1 plus C2 x power lambda 1 for e power lambda, z is log x. So, this is what you have if lambda 1 equal to lambda 2. So, these are the two linearly independent solutions in two different cases depending on the roots of your polynomial in lambda. Okay. So, we will see some example. So, simply take some 2 x square y double dash, solve this equation plus x y dash plus 3 y equal to 0. If you, how do we solve this? So, you can see second derivative will have x square, first derivative coefficient is x, 0th derivative that is y is the coefficient is constant. Okay. So, we will have a constant 2, 1 and 3. Okay. So, we can write, so now we can write x y dash, I can write dy by dz, x square y double dash I can write d square y by dz minus dy by dz, okay, where z is log x, say x positive. Okay. If x is negative you have to work with log minus x, same thing is true with log minus x. Okay. So, what you have, so this will give me, so you go and substitute, so you will have 2 times d square y by dz square minus dy by dz plus x y dash is dy by dz plus 3y equal to 0. This will give me 2 d square y by dz square minus 2 plus 1. So, you have plus dy by dz plus 3y equal to 0. So, you look for yz as e power lambda x solutions, then if you substitute this into this equation you will get 2 times lambda square e power lambda x lambda z, okay, and then plus lambda plus 3 times e power lambda z will be equal to 0. This cannot be 0, so that means this have a polynomial, has to be 0. This will give me lambda as minus 1 plus or minus square root of minus 24 divided by 4 2a. Okay. So, this will be minus 1 by 4 plus or minus I times root 23 divided by 4. So, if you choose this, so what are the, so these are two complex roots, lambda 1 is minus 1 plus I root 23 by 4, lambda 2 is minus 1 minus I root 23 by 4, where I is root minus 1, complex number, okay, imaginary number, imaginary. Complex number. So, you know the solution, the general solution does not matter, these are the two complex roots cannot be same. Okay. If the imaginary part is there in your complex roots, complex conjugate root cannot be the same. So, you have y of z, you can write the linear combination of these two, C1 times e power minus 1 plus I root 23 by 4 z, this whole thing with z plus C2 times e power minus 1 minus I root 23 by 4 z. Okay. So, this is equal to e power minus z by 4 is common. So, we will have C1 e power I root 23 by 4 z plus C2 e power minus I root 23 by 4 z. Okay. So, this I can rewrite as e power minus z by 4 times C1, you can write e power I constant into z as cos root 23 by 4 cos root 23 by 4 z plus I sin 23 by root 23 by 4 z. Okay. If you write, so you will get a new constants d1. So, you can write in terms of cos and sin, this you can write in terms of cos and sin, this also you can write in terms of cos and sin. C1, C2 are arbitrary. So, combination of C1 and C2, you will make C1 plus C2 as 1, that is d1 cos root 23 by 4 z, okay, plus here you get C1 minus C2 into I times C1 minus C2, that is your d2. If you call it as d2, you will have, you can write sin root 23 by 4 z. So, this is your general solution in a new variable z. Finally, you can replace z equal to log x, then it will become z equal to log x. If you would, the solution will be function of x, then this will be e power minus log x by 4 into d1 cos root 23 by 4 log x plus d2 sin root 23 by 4 log x. Okay. So, you can clearly see that x power 1 by 4, okay, 1 by x power 1 by 4 is e power. So, this whole thing I can replace with x power minus 1 by 4. So, this is your general solution because you have two arbitrary constants d1 and d2. This is the general solution. Of the given equation. So, you have seen here this is a special type of equation called Euler Cauchy type equation. So, this can be, you can get two linearly independent solutions just by converting it into linear equation with constant coefficients. Okay. So, this is one. Sometimes there are some ad hoc techniques. If you can reduce second order equation, so reduction some ad hoc technique, not always this is the ad hoc technique, not always it works, but sometimes nothing works, you can try this ad hoc technique. Ad hoc technique is called reduction method. Reduction to standard form, or putting into reduction to normal form. What I do is I convert this px y dash plus qx y equal to 0, I want in this form. So, y double dash, okay. So, I am changing the independent variable here by changing dependent variable. Changing dependent variable, what you do is you want this equation. So, changing y to u, some u, let us say. So, then you get an equation u double dash plus some fx, okay, let us call this something else, you will get into u equal to 0. So, this is u dash double dash is d square u by dx square. So, in this is the form you want. If you convert this, sometimes this fx, you can expect it to be constant. If it becomes constant, then you know how to solve this. That means you know how to solve this one. You know what is your y. If you know u, you will know what is your y. So, what is this transformation that takes y to u? So, what I do is let y of x is equal to some unknown ux, okay, so this is the unknown, this is the dependent variable, and some vx. This you know, you will know by making the first order term, you make it 0. So, you do not want that first order term. In this, from here to here, you made the first order term 0 by choosing in such a way that first order term will never appear into your transformed equation. So, this is the transformation you have. So, you simply put this y with u as a dependent variable, v is some function, okay. So, you simply u into v you substitute into the equation, you will get y dash is u v dash plus u dash v, y double dash is u v double dash plus u dash v dash plus 2v dash and then u double dash v. This is what you have, okay. So, this you substitute there, you will get u v double dash plus 2u dash v dash plus u double dash v plus p x times u v dash plus u dash v plus q x, what is y? U into v equal to 0. So, you want the equation in u. So, u double dash coefficients you collect. So, that is going to be u double dash is v, simply v, okay. So, you will have only v plus, now what is your v dash coefficients? U dash coefficients. U dash coefficients are 2v dash plus px v, okay, plus what is u? U is u coefficients. What are the u coefficients? V double dash plus what is u coefficient plus px v dash plus qx v equal to 0, okay. So, you divide with v, this is what you will get, okay. If I divide this with v, this is what you will get, okay. So, what I want, so how do I make this into that normal form? Normal form, I do not want this term. So, this term if I do not want, I have to choose v such a way that choose v such that this term is 0. So, that means 2v dash plus px v equal to 0. This will determine, this is the first order linear, is actually separable form, okay. I can solve this equation to find what is my v. Such a v I can choose, such a v I can calculate solution as a solution of this first order linear ODE, I can find what is my V. With that V I can make this term will become 0. So, I will have u double dash. So, this is the term we will have. Okay. Suppose this becomes, if this becomes constant for such a V, then I know how to solve my u. Once I know my u, I can calculate, I can just come back and put it here, that is my yx. Okay. So, this is how, this is the technique, ad hoc technique. So, by just reducing into normal form you can get your solution. So, what is your Vx? Vx is equal to, so dV by dx equal to minus Px V, okay, into 2. So, this you can write it as dV by V equal to minus Px by 2 into dx. You can both sides integrate, I just separated them. Equation is like dy by dx equal to fx into gx form. So, if we can do it, log V equal to minus integral pt dt, pt by 2 1 by 2 pt dt x naught to x, okay, and then this log both sides integrated from x naught to x naught. So, we will have log x naught, this is an arbitrary constant. Okay. So, this is equal to, this will give me what is my Vx. Vx is e power minus half some x naught to x pt dt, okay, into e power log x will be, sorry, this is actually V at x naught. This is arbitrary constant. So, this is going to be V at x naught. So, this you can choose it as 1, because if I choose it as 0, if I choose as my V, then y is 0, 0 is that you do not gain anything. So, you got only, I know that homogeneous equation has a trivial solution. I am looking for non-zero solutions, because you are looking for 2 linearly independent solutions that has to be non-zero. So, I have to choose my Vx constant as 1, so non-zero. So, you can take it as 1, so that this is your V. With this transformation, if you can calculate this term, if this is a constant, then you can get your solution. So, you know how to find, this has gone, that means this term has gone. So, u double dash plus some constant into u equal to 0, that you know how to solve. Okay. So, I can give you an example. So, this is called the reducing into normal form. In some cases it works, because you are reducing that equation linear second order linear ODE with variable coefficients, you are converting into equation with constant coefficients of second order, but without having second order term, okay, first order term, first order derivative you are removing it, you are putting in such a simpler form by choosing some transformation. So, we will see example later. Okay.